Hello, welcome to Fundamentals of Acoustics. Today is the fourth day of the current week, and today as well as during the remaining portion of this week, we will develop a mathematical formulation which we will use in the subsequent week to figure out what type of frequencies and to what extent particular frequencies can be handled by devices such like mufflers or silencers. And specifically, we will be looking at the performance of reactive mufflers, where the sound as it passes through the muffler, it does not get absorbed, but rather it gets reflected back into the sound source. So, we will be, because there are two types of mufflers. One category is reactive muffler, where sound pressure as it enters the muffler, it gets reflected, and in the other type of mufflers which are known as resistive mufflers, the sound as it travels through the length of the muffler, it slowly gets absorbed and gets out of the muffler at a much reduced sound pressure level. So, starting today, we will lay down the foundation, the mathematical foundation for reactive mufflers. So, to solve the problem of a muffler or to develop a mathematical model of a reactive muffler, we have to solve a particular type of problem known as 3 media problem. So, once we learn how to solve this 3 media problem, we can relatively easily use this knowledge to design a muffler of our choice. So, what is a 3 media problem? A 3 media problem is, so first thing is that it deals with one dimensional planar waves. Okay. So, what we are trying to understand is that suppose there are 3 media. So, medium is singular and media is plural. So, this is medium 1, first medium, this is second medium, third medium. Examples of these 3 mediums could be, here I may have air, in region 2 I may have carbon dioxide, in region 3 I may have nitrogen, whatever. And these 3 media are separated by sharp boundaries, 1, 2 and 3. Okay. So, these are the boundaries. So, as sound, so our aim is that if there is an incident wave in the first medium and the complex pressure due to the incident wave alone is P plus E minus J omega T, oh it is plus thing, minus K1x, okay. So, K1 is the wave number for the first medium. So, suppose the incident wave is of this nature, then this sound, some of this sound will get reflected, some of it will get transmitted into 2, and finally some of the wave will get transmitted into 3 and it will move out. Okay. So, let us say the transmitted wave is Pt E j omega t minus k3x. So, what we are interested in understanding is that what is this ratio Pt over P plus, that is what is the main issue. So, the problem is that if we know P plus and we also know the properties of medium 1, medium 2, medium 3, and also if we know the length of the intervening medium which is medium 2, then can we figure out the ratio of Pt and P plus. That is our fundamental problem. So, this is a 3 media problem because there are 3 media involved. Now, in context of this particular problem, I will not use terms P plus and Pt because there will be several P pluses and P minuses. Rather, in medium 1, I will use the term, so the incident wave amplitude is A1, and then as this wave hits the boundary, part of it gets reflected, and the complex pressure amplitude for the, or complex pressure for the reflected wave is A2 E j omega t minus k2x. Oh, sorry, it is k1x. So it will be plus k1x. Now, so some of it will be reflected and then some of the sound will get transmitted into medium 2. In medium 2, the incident wave hitting at the next boundary is A2 E j omega t minus k2 x, and the reflected wave is, so I am sorry, so this should be B2, actually it should be B1, and the reflected wave is B2 E j omega t plus k2x, and finally the wave which is getting transmitted out of medium 3, its complex magnitude constant is not Pt, so that rather we will call it A3. So what we are looking at is the ratio of A3 and A1. Now some important things to note. First thing, as sound is propagating from traveling from medium 1 to medium 2 to medium 3, the frequency, so omega and frequency, it does not change. In 1, 2 and 3. Why will it not change? Suppose there are some fluctuations happening n number of times in medium 1, then the adjacent medium in adjacent air particles or medium particles in medium 2 will also get oscillations at the same number of times, right? Their amplitude may go up or down, but the oscillations will remain the same, because if I am hitting some particle 100 times, then the other adjacent particle will also vibrate at the same frequency. So frequency as I move from medium 1 to medium 2 to medium 3, it does not change. Second, these three media have different material properties. So the pressure, ambient pressure in these three could be different, or the density could be different. So C1 is not equal to C2, is not equal to C3. Densities of these three media need not be same, right? Because what is C? C is equal to P naught gamma over rho naught. If I have air, nitrogen and carbon dioxide, there is no reason to think that C has to be the same. Similarly, rho 1 is not necessarily equal to rho 2, is not necessarily equal to rho 3. And because rho 1 C1 is characteristic impedance for the first media, so for the same reason Z1 is not equal to Z2 is not equal to Z3. Third, if frequency is same but velocity of sound is different, then lambda 1 is not necessarily same as lambda 2, is not necessarily same as lambda 3. Okay. So, and if lambda is not same, then k1 is which is equal to 2 pi over lambda 1 is not same as k2, is not same as k3. Okay. So for that reason, we have three different wave numbers. in our expression, and for the reasons discussed here we have same angular frequency in our formulation. So, this is important to understand. So, we have used these assumptions as we have written down expression for incident and reflected wave for each of these media terms. The last assumption is that there is no reflection in medium So, there is no reflection in the third medium. So, that is also something which we have incorporated into the model. Now, our aim, I will go back, is to find out, for starters, is to find out the ratio of A3 and A1. So, how do I do that? We once again we go back. So, this is again a one dimensional problem, all the waves are propagating in one direction, planar waves. So, we once again go back and use transmission line equations. So, we will get two transmission line equations corresponding to medium 1, 2 from 2 and 2 equations from the third and 2 equations from the third medium. Okay. So, overall we will have 6 transmission line equations, but then how many unknowns we have? A1, B1, A2, B2, A3, so 5, and then of course K1, K2, all these things are also unknowns. So, we have more unknowns and less number of equations. So, we need some additional conditions. So, those additional conditions come from the interface. Now, before we talk about the interface between medium 1 and medium 2 and medium 2 and medium 3, let us define our coordinate system. So, our coordinate system is such that this is the direction x, and at this first interface x is equal to 0. Okay. So, let us look at the boundary conditions which will give us the extra conditions. So, the first boundary condition will be that at x is equal to 0, consider a point, particle of fluid here and another particle of fluid. So, let us consider this point as x1 and this point as x2, and x1 and x2 are extremely close to each other. Actually, the distance between them is theoretically infinitesimally small, actually it is 0, and what that means is that whatever is the velocity of the system at point x1, it has to be the same at point x2. So, what that means is velocity is continuous at interfaces. Same thing is true for points at the second interface. So, this is let us say x3 and let us say this point is x4. So, the same thing is true at the second interface. The second consideration is on pressure. Now, consider the situation where pressure at x1 is different than pressure at x2. If it was different, what is the distance between these two points? Theoretically it is 0. So, you have a non-zero pressure difference at 2 points which are separated by 0 distance, which means that the acceleration between point x1 and x2, because there is very less mass contained between 0 mass, if there is 0 distance, the mass contained in this is 0, but pressure is non-zero, difference in pressure is non-zero, which means that the fluid will accelerate at infinite acceleration. M times A equals change in difference in pressure times area. Difference in pressure is non-zero, area is non-zero, mass is 0, so acceleration has to be infinite. So, that is not physically possible. So, what that means is that pressure cannot be different. So, essentially it means is that pressure is continuous at interfaces. Okay. So, how many conditions we get? We get two conditions at the first interface, which is V1 equals V2 and P1 equals P2, and two conditions at the second interface, P3 equals P4 and V3 equals V4. So, total of 4 extra conditions, So, this is what the overall problem is. What we will do is we will start solving this problem in our next class, and that is tomorrow and also day after tomorrow, and then we will draw some very important conclusions from such an analysis. So, with that I close for today, and we will meet once again tomorrow. Thank you.